This is Electric Universe Eyes, and today I'm going to narrate from the book Electric Universe, written by David Bodanis. Page 233, Mr. Amp, Mr. Volt, and Mr. Watt. The world is made of electric charges, and our technologies operate through electric charges, and even our brains are powered by electric charges. Yet how to measure the flow of electricity? Three historical characters have had their names immortalized in the familiar units amps, volts, and watts, which describe and summarize what's happening inside all the electric devices we use. The first was the French mathematics professor André-Marie Ampère, who in 1820 studied the way that rushing electrical currents created magnetic poles. It was one of the only satisfying moments in his life. On his tombstone, he had the phrase "Tandem Felix," happy at last, inscribed. But in 1881, long after his death, the word amp was taken to measure the flow of charged particles. In ordinary household circuits, it's simply a count of how many electrons are passing through a given point in a wire each second. When 6 quintillion, that's 6 0.00000000000000000 electrons pass in a second, then we say that 1 amp of current is flowing. When 12 quintillion electrons travel through the wire, we call it 2 amps of current. An electric bulb lights up when a single amp's worth of electrons, 6 quintillion individual electrons, are passed along each second. Switch on a car's ignition and 50 amps worth of electrons, 300 quintillion electrons, pour into the spark plugs each second. The second character was the prickly Italian Alessandro Volta. He created the batteries that allowed other researchers to investigate the force that can push all those electrons along. Though, as we've seen, we had little understanding of why those batteries worked. Michael Faraday's explorations helped make sense of that pushing force, and the key concept for measuring it came from Macquorn Rankine, a friend of both William Thomson and Faraday. Rankine had spent years designing railroads for the rolling hills of Scotland, and he used that experience to help come up with the notion of what he termed potential energy. A train high on a hill might not be moving fast, but it has a lot of this potential energy, for once it starts down the hill, it'll pick up speed thunderingly fast. Rankine and Thomson used that vision to try to look into the force fields they imagined stretching out from batteries and other electric sources. In their mind's eye, there were invisible hills where the field was strong and valleys where it was weak. Put a charged particle where the field is strong and it'll hurtle away, like happily startled train passengers who see their locomotive leading them fast down to a waiting glen. A volt, Rankine and Thomson realized, should simply measure how steep and how strong this pushing force is in the topography of one of Faraday's invisible fields. An amp measures how densely a current of electrons is flowing. A volt is the downhill pushing force that creates this flow. The last of the three characters was James Watt, yet another ingenious Scot, and the patron saint of electric bills. Although he hadn't quite invented the steam engine, he had improved it greatly and decided that his major achievement would be to persuade tight-fisted mine owners to actually buy this new machine. What he needed, he realized, was a risk-free offer, showing that their savings from the new machine would more than offset the cost of buying it. But for that, he needed to measure the savings, which meant he had to find a catchy way of summarizing what the horses dragging the carts and driving the pumps in the mine were doing. He found that a horse could tug a 500-pound weight quite steadily and came up with the idea of horsepower, the rate at which an average horse could keep working through a long day. If he could offer a mine owner a steam engine that cost less than a horse and its feed, yet would operate at more than the rate of 1 horsepower, then he realized he had a chance of making a sale. With the spread of the metric system, his original term was replaced most justly by the term watt. Horses are strong, and the power of a single watt was defined as a small fraction, just about 1/750th of a single horsepower. Today's DJs don't use horses tugging on pulleys to spin their recordings or pump their speakers, but when they say they're going to power up a 750-watt sound system, they're basically saying that their equipment needs as much power as a single tugging horse could provide. A watt simply measures the power that the pushing volts and scurrying amps will provide. In the time of Mr. Watt's descendant, Robert Watson Watt, Britain's radar defense depended on being able to compute how this accurately measured power would travel through the air. The sky is loaded with electric charges, yet they're so tightly bound up with one another in air molecules that even a powerful radio wave shooting upward won't be able to drag them apart. Only the far stronger force fields emanating from huge storm clouds can do that, to begin the crackling of a lightning bolt. But would the weak beam of a radio broadcast be enough to tug loose at least some of the electrons in a soaring metal airplane? That's what Arnold Wilkin had to compute in SLO in 1935, and he used Mr. Watt's ideas and the clear definition of watts that the original definition of horsepower provided, to work out that there would in fact be just enough power transmitted outward to make those electrons transmit a detectable answering signal back toward the ground. Power measured in watts would fly up. A field with a pushing force measured in volts would accordingly appear around the plane, and a flow of electrons measured in amps would start up inside the airplane's metal wing strongly enough, Wilkins computed, to create the answering signal on which Britain's radar defense could depend. Go get this book and read the notes. It's excellent.